Hey, don't be fresh.
Okay. And the videotape's rolling. So what we've got here, the combined gas law, Avogadro's principle, and we can link that all together into the ideal gas law, and Sam's baby naming balloon story is a perfect fit. No, it's okay. The one piece of the puzzle that's new is R. R is a universal gas constant. It comes in different varieties, if you will, and we'll talk about which one to pick when. Up on the screen again, you can combine those gas laws into a single gas law known as the ideal gas law, which is PV equals nRT. Pressure can be in atmospheres, typically not pascals. Kilopascals, torr, millimeter of mercury. Temperature must be in Kelvin. And I'm happy to say very few kids forgot to convert to Kelvin. There's always a couple, but I don't think it was in here. The volume must be in liters now. Remember, 1 liter is 1,000 mils. N is the number of moles. And R is the universal gas constant. And the universal gas constant that you will select is based on the units of pressure. If the units of pressure are atmospheres, then you will select this constant. If the units of pressure are in kPa, then you will select this constant. If the units, say it again.
If it's in PA, would you also do that one too?
But you'd have to make a conversion to kPa.
Well, I'm just saying because there's no PA.
Exactly, but you'd have to get the units. If they gave you units of pressure in pascals, then you would need to convert to kPa. Divide by 1,000. If they give you torrs, you'll use this constant. If they give you millimeters of mercury, this constant will work as well, because 1 torr is 1 millimeter of mercury. And these gas constants, but I really didn't get that tricky with it. These gas constants are provided to you on the back of the periodic table, so you don't need to memorize them. And again, the R that you will select is based on the unit of pressure. And one of the kids was very confused by this last period. So if I'm rambling and you don't know what I'm saying, then you need to ask, please. Go ahead.
Why is there an L?
Why is there a what?
Liters.
Liters.
So liter to atmosphere to moles.
No, so the unit, right, it looks funky.
It's very funky.
So it's bothering you, so let's explain it. If you solved for R, you would have PV over NT, correct?
Yes.
Okay, so let's say your unit of pressure is atmosphere. The volume must be in liters, moles, Kelvin, and that becomes your unit. It's atmosphere liters,
Oh, and then that's
mole Kelvin, and when you write it out, you usually put dots there, but when you print it, like type it, usually put a dash in between when you multiply the units. So that's where the units come from, and it's a great question. So if you have kPa here, then you'd have kPa here instead, or if you have torr here, then you'd have torr here instead. And it's very, very rare that you solve for R, although in your second lab for this chapter, you will be solving for R to show, to try and prove the ideal gas law, and you'll see it actually works quite well. We'll be emptying out lighters, collecting a certain volume of gas, determining the pressure of the gas using Dalton's law, etc. Okay? So we have PV equals nRT. That is known as our ideal gas law. And a few things you want to note right away. The temperature, of course, has to be in Kelvin. The volume has to be in liters. And they usually give you milliliters, so make sure you make the conversion. This is where following through on units is really important.
It's 1,000.
1 liter is 1,000 mils, or 10 to the third. The other variation that I want to mention up front here, there's another one we'll get into in a little bit. But if, for example, you were given the mass of something, let's say you had 30 grams, what gas do you want it to be?
Neon.
Neon, fine. In order to get to moles, you know you'd have 1 mole of neon is 20.180 grams of neon. And that'll give you moles, correct? Okay, so basically what you're doing here is you have the mass of neon divided by the molar mass of neon. This is in grams, this is in grams per mole. That's equal to moles. So instead of putting N here, I can replace that N
Little M over.
exactly. You can put M over big M, make the distinction clear, RT, where this is the mass in grams, this is the molar or molecular mass off the periodic table. The other thing I'm not sure why this isn't clear to you, maybe you can tell me, is some of you are confused with fractions. You can extend this out, right?
Yeah.
Yes? Okay. So these are two formulas. The kids are like, well, what are you going to give me? I'll give you PV equals nRT if you want, but you have to derive that. Yes?
What is the difference between little m and big M?
Little m is the mass in grams, and the big M is the molar or molecular mass off the periodic table. And I did try and write that in your notes for you. Go ahead, Chris.
So since you need pressure, like the ATMs, in order to find your R, they'll
Okay.
always give you pressure and you want to solve for it? Or?
Now, they can ask you to solve for pressure. If they don't specify a unit, pick whichever R you want. If they do specify a unit that they want the pressure in, you'll pick the R that corresponds with it. And I gave you an example, and we'll go through that one. Okay, before I link density to this concept, I want to walk through numbers 1 and 2 with you, and I'll let you shoot at 3, and then I'll walk through the density piece with you. It's really a very, very short lesson, just a lot of problem solving, and then you'll have time to do some problem solving. And again, I know some of you probably have not done any classwork since your last quiz. That's going to come back and bite you. This is the hardest quiz of the quarter coming up. All right, this really tells me whether you're ready for AP Chem, for those of you who signed up. Okay. Number 1 says 0.0300 moles of gas. So that's your N. Occupy 500 mils of space. What's that? Volume. Do we want it in mils or liters?
Liters.
Better be in liters or you're done. At 2 atmospheres of pressure. So if you have 2 atmospheres of pressure, and then you want to calculate the temperature, I'll come to that pressure thing in a minute. My mind went too fast. When I work through these problems, I always write down all the variables. That helps me keep track of everything. But more than that, it helps me determine which formula is most appropriate to solve the problem. So what we've got here is N is 0.0300 moles. The volume is 0.500 liters. The pressure is 2 atmospheres. The temperature is what we're solving for, and they didn't specify how they want the temperature, so you really can keep it simple and solve it in Kelvin. Don't make more work for yourself. Based on the fact I have PVN and I'm looking for T, that tells me that I'm going to use PV equals nRT, because that's going to make it the simplest for me. Thank you. Now I'm going to solve for temperature, and this is what I'm seeing. You're not having chemistry issues. You're having math issues. Some of you have terrible difficulty manipulating variables in an equation. You're solving for T. N and R are multiplied to it, so the way to undo that is to divide by those, correct? So we're going to have NR here now. And the temperature is equal to the pressure, the volume you need in liters, or it's not going to cancel. I'll show you that in a minute. The N and the T. No, not the T, the R, right? And which R should I select? The one that has ATM in it. So that's 0.0821 liters atmosphere over mole Kelvin. And again, those will be provided to you, so you don't need to worry about that. In your calculator, you will need to bracket off the denominator so that you can solve it correctly. So what we've got here, basically have 2 times a half, which is 1, divided by open parentheses 0.03 times 0.0821 close, and that's going to be 406 Kelvin. Maintain the least number of sig figs with multiplication and division. Pretty straightforward. Again, you have to be able to manipulate variables. Questions on the first one? So the volume has to be in liters. The R you select will be based on the pressure. All right. In number 2, it says argon occupies 100 moles of space at 80 degrees Celsius and 203 kPa. What mass of argon is present? I need a volunteer to help me pick out the variables. I'll pick my own volunteer. All right, Abby, go ahead.
I would have the questions and
Here you go. It's at the top of the screen.
100 milliliters, which you actually go to liters, is the volume.
Okay, so 100 mils would be 0.1000 liters. Then what?
Convert 80 degrees Celsius to Kelvin and now the temperature.
353.15 Kelvin is what T is equal to. Next.
203 kPa is the pressure.
Good.
And 125 N.
They're asking for the mass. So that's baby M, right?
Oh, yeah. So you can find the
All right, so that's what I've got. I was writing as she spoke. You can see what I pulled out. Make sure you pulled it out like I did. Okay, so in this case we're looking for the mass. So instead of using PV equals nRT, I'm thinking PV is equal to the mass over the molar mass, RT, because I can go ahead and manipulate that and solve for the mass. I know the substance, so I can get the molar mass off the periodic table. So what I'm going to do here, multiply by molar mass, and then divide by RT. And you should have a high comfort level manipulating variables in an equation based on the math that you are in. So the mass is equal to the molar mass. Argon on the periodic table is 39.95 grams per mole. The pressure is 203 kPa. The volume is 0.1000 liters. And you'll divide that by RT. Which R should I use? The 8.314 liters kPa over mole Kelvin. And then temperature is 353.15 Kelvin. And I get a mass of 0.276 grams. That's the mass of argon. Now, if you have difficulty with that formula, you can solve for moles and just convert to mass by multiplying by the molar mass off the periodic table. Whatever's easier for you is the way to go. I would like for you to try number 3. Uh-huh. 0.276 grams, is that what you got? Okay, good. So again, get those variables out, figure out which formula is going to suit your needs best, and let it rip. Ready? Not yet?
Very much not yet.
Very much not yet? All right, if you're not done, don't look up. You wanna know the answer? That's what I got.
You can do it in different, like if you plug in a different arm, you get a different
Except you're supposed to.
But you can't plug in a different, okay,
you can.
well, they asked for Tor, right?
Yeah.
So you could get what you got, but then you would convert it. So that's okay, but that's more work.
Where'd you get that 44.009?
Molar mass of carbon dioxide off the periodic table, 1C, which is 12, and 2 O's at 32 is about 44.
How do you know you need to use the little m over big M?
I would use that because they gave me mass. You could get to moles if you wanted to and do PV equals nRT, but to me it's easier to plug everything in at once. And watch the units as they cancel.
We might have done a problem like this, but I'm just not remembering. Will they give it, like, what units do we look for if they give us an actual just N and we don't have to do little m over big M?
They'll give you moles.
Okay.
N is for moles. And if they give you millimeters of mercury, you can convert to atmospheres. 1 atmosphere is 760 millimeters of mercury. Although the torr factor here, you could replace that actually with millimeters of mercury too. So whatever's easier. All right. The next thing we want to talk about we have PV equals nRT, that's the ideal gas law. We have PV is equal to little m, that's the mass in grams, over big M, molar mass off the periodic table, or molecular mass if you have a covalent compound, RT. What is density equal to? Mass over volume. So if I manipulate this formula where I'm going to interchange these two variables, what can I replace m over v with? D. So this is a way to integrate density into the ideal gas law, because we know density is mass over volume. So PM is equal to DRT, and there are a lot of cutesy little ways to remember this. And again, I'll give you this if you want it. I think you probably can learn it, but I'm not going to give you all the other variations. This one's very easy to remember, and it's just silly, and if it's offensive, I apologize in advance. So some girls suffer from PMS, so you're putting the P and the M together, and some boys are very, very dirty, so you got the DRT together over here. Now if you think of something cuter, by all means, as long as it's clean, share it. But pressure times molar mass is equal to the density times the universal gas constant times temperature. And again, the units of P will determine the R you select. So we can use this formula, and we will if we're solving for density or density is given and you know the gas. So in problem 4, you're going to see the usefulness of this particular formula. Number 4 says calculate the molar mass, that's what we're looking for, of a gas that exerts 2.50 atmospheres of pressure at 150 degrees Celsius, and the density is 0.780 grams per liter. So again, let's get that information down. On number 4, we're looking for molar mass. The pressure is 2.50 atmospheres. The temperature is 150 degrees Celsius, or we know that we better get to Kelvin right away so that we don't do anything silly. The density is 0.780 grams per liter. And we know that PM is equal to DRT. And if I want to solve for M, what do I divide both sides by? So we're going to divide by P. And now watch your units as they fall into place. Which R should I use? This one. How come? Because it's got ATM in it, atmospheres. Temperature. We have 0.78 times 0.0821 times 423.15 equals divided by 2.5, and I've got a molar mass of 10.8 grams per mole. And if you see your units, you'll see how that falls into place. The liters cancel, the atmospheres cancel, the Kelvin cancel. You have a unit of grams per mole, which is a unit of molar mass.
With that, can you also determine what atmosphere?
You could, but in this case, with that kind of, that molecular mass is so small, it doesn't correspond to anything because boron's not a gas. So that would be tricky. Don't really think you could come up with a gas that has that small of a molar mass because you have hydrogen and helium, but they're smaller. But yeah, you could match it up to something. Questions here? Yeah, in a sec. Questions here? Okay, I would like for you to do 5 and 6. You have all the tools now. Are you just looking for the answer to 3? 333 tour? 333 tour? If you didn't get that, look at what I have here and make sure that you match. Try 5 and 6. I'm going to put them at the screen. If you didn't get 3 yet, you can either copy it in a few minutes or just look at a neighbor's. I just want to put this up in case kids don't have their notes today. So 5 and 6. See if you can do those. We'll check answers. If you're having issues, we'll address them, and then I'll tell you what classwork goes with this, and you'll have some time to work through that. Alright, I'll reveal 5. I won't show 6 yet. So here's 5. How'd we do with 5? Yes on 5? Good? You have the right unit too?
I'm plugging the exact thing into a calculator.
Alright, so if it's not coming out in your calculator, are you putting the parentheses in red?
I'll do it again.
It's just divide the top of like 624.
How are you getting 624?
780 times 0.8.
Yeah.
625.
Was I doing divide as well?
Yes on 5?
Okay, I did number 6.
Yeah, you could have gone after density that way if you wanted to. Whatever's easier. Can do it either way. Alright, I'm going to give you a few minutes to finish up 6. I just want to wrap it up and then give you time and tell you exactly what you should have done before the next class. So your answer to 5 is here. If you haven't finished 6, don't look up. If you haven't finished 6, don't look up. So the answer to 6 is here. And this lesson in your classwork corresponds, that's classwork 3.2b, 4 through 10. And through 10, including 17, should be done for the next class. Because in the next class, we're going to link the ideal gas law back to stoichiometry, as well as the combined gas law with stoichiometry. And that'll allow us to use gas laws to determine some variable, and then the mass of a solid or a liquid we can link back to with stoichiometry, or we can do volume ratios as well. So we'll be taking a look at that in the next class. Today you should have an understanding of the ideal gas law, how it links pressure, volume, temperature, moles, and R, the universal gas constant. Chris? Sulfur trioxide, guys, sulfur trioxide is a covalent compound. A covalent compound you write as it sounds, sulfur trioxide, so it's SO3. Sulfite and sulfate are ions, but you could have, for example, hydrogen sulfate, hydrogen sulfite, you could have sodium sulfate, etc. So when you just have two nonmetals together, you have a covalent compound. So here's 5, here's 6. We still have quite a bit of time before the bell rings and before Beauty 101 starts and everything else. Classwork 3.2b, 4 through 10, and I want to get your quizzes back to you. So 5 and 6 should be done. Classwork, you should have a pretty solid understanding of the ideal gas law, and this is just one of many laws that we've talked about in this chapter. There's a very big cumulative effect here. Make sure you understood the beginning parts because it's starting to build. And when you take your quiz next week, it's going to cover Dalton's law of partial pressure, the combined gas law, Graham's law of effusion, the ideal gas law, and then we'll link stoichiometry to one of the gas laws as well. So the quiz is very broad. It covers a lot. And then the test will cover the entire chapter, including a couple baby questions from nuclear chemistry. So that'll be a little more challenging. I think it will be the hardest quiz of the 9 weeks and the hardest test. So stay on top of it so you're successful.